Welcome to my video about the shell method, which is a tool used to find the volume of a solid of rotation. So by now you've probably covered finding volume through cross-sections and disks and washers, but sometimes you will need to know the shell method in order to solve some volume problems, and sometimes it just makes it a lot easier. So let me start by introducing the concept behind this method by using some visuals. So if we wanted to determine the volume of a solid generated by revolving this gray region around the y-axis, we could determine it by using shells created by very thin rectangles, as denoted by these red lines, about the y-axis, which produces a shell, a cylindrical shell. See, the idea behind this method is that if we start to accumulate the number of shells, it will approach the volume of the solid. So each of these red lines represent the height in one of these cylindrical shells. So, as the number of the shells approach infinity, we approach the volume of the solid. So basically what we're doing here is accumulating a bunch of these, finding the volume of each cylindrical shell and getting the summation, which is allowing us to find the total volume of the solid. So the shell method is used to find the volume of a solid of revolution. It is called the shell method because it uses cylindrical shells. So let's take a closer look at just one shell. So if I wanted to rotate the region bound by the x-axis, the y-axis, and the function right here is denoted by this black line, it would produce a solid that looks something like this. And this cylinder would represent one shell that we would use to determine the volume of the solid. So if we cut out this cylinder and spread it out, lay it out, and we would get this rectangular prism. And now you're probably wondering, if we spread out a hollow cylinder, wouldn't we get a rectangle as opposed to a rectangular prism? But actually there's a width to this very thin width. It's infinitesimally small actually, but that width nonetheless requires us to find the volume of a rectangular prism. So the length of the rectangular prism would be the circumference of the cylinder, which is 2 pi r. And we'll note that as 2 pi x. And the height of the cylinder will be the function essentially, which we'll denote for now as h of x. And the width, this infinitesimally small width, will be denoted as dx, the change in x. So essentially what we're doing here is finding a bunch of these rectangular prisms and their volumes and adding them all up, and we should get the total volume, correct? So here's the integration from a to b, the summation of the volume of one cylinder. And we all know that the volume of a rectangular prism is length times width times height. So let's multiply these three, and that we should get the volume of one cylinder. So 2 pi x, which is the length, h of x, which is the height, and d of x, which is the width, and altogether that's the volume from a to b integrated is the volume of the entire solid. So just to change this around a little bit, we can pull out the 2 pi and change h of x into f of x minus g of x, because h of x is the height, which can be found by subtracting the lower function from the greater function. So just to sum things up, here's the final equation that we're going to be using when revolving a function. So just to sum things up, here's the equation that we'll be using when revolving around a vertical axis. So I'm going to define some of these variables once more. So x is the distance from the center of the rectangle to the axis of rotation. It's essentially the radius. And the f of x minus g of x is the height, which is denoted by the function in this case. And the d of x is the infinitesimally small width. And just as a side note, the rectangle created, and you should always draw a diagram before approaching a problem, the rectangle drawn is also always parallel to the axis of rotation. So the axis of rotation is the y-axis in this case, which is vertical. So the rectangle will also be vertical. So you should use a shell method when the axis is perpendicular to the axis of revolution. So for example, when the axis of revolution is a y-axis, but you need to integrate a problem using dx, then it would be preferable that you use the shell method. And this works vice versa too. If the axis of revolution is the x-axis, but you need to integrate using a problem with dy, then you should use the shell method of integration. And let's look at this problem, a situation where it would be so much easier to use the shell method. So in this curve, let's pretend that it is defined in terms of dx, and you are revolving around the y-axis. So you should use the shell method anyways. But if you notice, using a washer method, you wouldn't be able to solve this problem very easily, because first of all, the inner radius diminishes and disappears after a while. Also, it would be hard to differentiate the two different radius considering that this is one function. So if you look at the top view of this type of curve, it would look something like this when revolved around the y-axis. So as you can see, this dip does not fully go through, which means that the inner radius diminishes after a certain point. So in this case, it would be much easier to use the shell method of integration. So let's start with our first example problem. What is the volume of the solid revolved around the y-axis bound by y equals 0, x equals 2, and y equals root x? So always start by drawing your diagram first. And it's good to draw the rectangle because that really helps visualize so you don't make any careless mistakes. So let's start filling in our equation that we're given when revolving around a vertical line, which in this case is true. So we go from 0 to 2, because that's our boundaries on the horizontal. So from 0 to 2, x is just x because the distance from the rectangle to the axis is x because the function actually touches the y-axis. The height, however, is y equals root x, and because the lower function is 0, it'll stay root x throughout the process. So you end up with this equation, and if simplified, this equation. And if you integrate and solve through the boundaries, you should get 4.525 pi. So we just worked a problem that rotated around a vertical line. But now the next problem we're going to approach will be rotating about a horizontal line, and also the axis of rotation will not be the y-axis or the x-axis. It's going to be a little bit different. But the only changes between a vertical line, rotating about a vertical line, and rotating about a horizontal line is the variables. So just change x to y. So when rotating about a horizontal line, this is your equation. And just to review the variables, so the y is the distance from the center of rectangle to the axis of rotation, and the f of y minus g of y is the height of the rectangle, and d of y is the width. So y is essentially the radius once more. So here's example 2. What is the volume of a solid revolved around the line y equals -1, bound by x equals 0, y equals 2, and y equals root x? So we want to start by drawing your diagram. And what you'll notice that the axis of rotation is now horizontal, which means that our rectangle is also horizontal, and we'll need to use the equation that involves y instead of x. But it's essentially the same concept, so the process would be similar. So first, let's find out what y would be. So y in this case, the function doesn't exist past 0. So as you can see, we will need to add a value to y in order to get the full radius that extends from the rectangle to the axis of rotation. So the y goes from here to here. So what do we need to add in order to make this length equal the to make it the full radius? We'll have to add 1 to y plus 1 because 0 to 1 is 1. So y plus 1 will get us the radius, or the y, so substitute y plus 1 for y in this situation. And the f of y minus g of y is the height of this function. However, we need to change our values. So y equals root x, we need to change it in terms of y, so change it to x is equal to y squared. And so y squared minus the lower function, but the lower function is x equals 0, so that shouldn't change. So if you factor out and simplify and integrate, you will get this equation and solve for through your boundaries, and you will get 40 pi over 3. So that was the end of the shell method integration tool presentation. What you really need to remember is basically just this concept, because you can really make this set up this equation by yourself just by understanding the concept that one cylinder, open it up, find the volume of this rectangular prism, and find the sum of a bunch of these from A to B, an infinite amount of these actually, and you should be able to find the equation by yourself. Just by knowing, just make sure that you know what your variables mean, and make sure that your rectangle that you create when making your drawings is always parallel to the axis of rotation. And just by remembering these few hints, you should be able to get the use the shell method in order to find the total volume of a solid. Thank you.